Welcome to another episode from the Ed of Ed. This is part 2 of the Brandy's 1920s headset series. An episode I guess you could call part 0. Some months ago I did an episode on restoration of the Bakelite ear caps. Check that video out in the description below if you want to look at that. It was especially handy perhaps for folks that have these sort of headsets with the Bakelite earpieces that are broken. Anyhow, in episode 1, I looked at the audio quality of my headsets as far as audio frequency response and also just general music playing back quality. Looking at the graphs here, you can kind of see that the frequencies taper off rather rapidly after about 3 kilohertz, which is not too surprising, and that the left-hand side appeared to be weaker than the right-hand side. Okay, as a quick experiment, see if it's of any value or not. I have this plastic material I bought quite a long time ago that has ferrous material in it. And if you put it in a magnetic field, it'll kind of follow the lines of the field. And it's good for visualizing magnetic fields. So let's see if this picks up anything and see if it's of any value to research anything. And you can kind of see something there. And I don't know if I get much more out of it than that. Let's see, that's that side. And see if that helps any on this side. And well, it's interesting anyways, but I don't know if it really tells you anything. Let's see here. I don't know. Yeah, I was kind of hoping for something a little more dramatic than that, but it doesn't really tell me much other than, you know, obviously it's the 2 end poles of the coils is obviously where the field from the permanent magnets come up, because, you know, these coils aren't energized. It would be actually kind of interesting once I'm running the headsets with some signal through them to see what that looks like. It'd be interesting to see if you can actually see anything. So I guess the next thing to do would be to try and at least figure out the polarity of the poles. And it looks like that is north on this side, and it's definitely south on that side. Okay, so that's pretty straightforward. I guess we can mark that anyhow. See if I can get a magic marker here. We'll say north. I guess it's actually opposite, but we'll call it north-south. I know it's actually opposite, but okay. So this side here, it appears to be the south side, and north. I'm just going to say that that's north. I know it's actually obviously opposite fields attract, but anyhow, that's the direction that the compass is pointing towards it. Okay, alright, so there's that. So we have north, south, north, south. What can we do with that? I don't know. We'll figure that out next here. I guess the next thing would be, is there a way to determine field strength? Okay, so what I have here now is kind of a crazy idea I'm going to try. I have the one of the transducer earpieces of the Brandy's headset on a little stand here, and I've rigged up this other little calibrated slide stand. It moves in thousandths of an inch. It's just all taped together. It's nothing. Not a lot of great deal of trouble has gone into it. And I've got a couple pieces of scrap plastic, and I put it on there, and I got this guy situated such that it can just barely touch on that. It's at 1/8 of an inch. Now the idea is I'll take the diaphragm, the steel diaphragm, center it up in here, center this guy up, and then start to move the diaphragm up towards, just like that, up towards this headpiece, and see at which point the diaphragm springs up onto the pull pieces of the magnet and get a distance measurement, and maybe that will tell me the magnetic field strength between these two. Odds are this won't work because it's nowhere near enough resolution to do that, but the variations in setup will almost certainly wipe out any precision there. But I'll give it a try, see what happens. I'm optimistic about it. You never know, I learned something new. So let's give this a try. Okay, so here's the right hand side. One of no doubt many runs I'll have to do in order to find out if this is repeatable. And we'll start moving this up until it jumps. There's 25 thousandths. So now moved up 50 thousandths. There we go. 5, 6, 7, 8 looks like. 58 thousandths. And we'll repeat this ad nauseum number of times and then try the other side, and I'll give you a result. Okay, after quite a few runs of the right hand side, which averaged pretty much right at 58 thousandths, jumping up, we'll see if there's any measurable difference with the left hand side here. Here's 25 thousandths, 50, 50, yeah. That's interesting. That's 8 thousandths less, and once again, I thought this was going to be the weaker magnetically side. So a few more of these runs, and we'll see what I can conclude. Left hand side reset again. Ah, 48. Not sure what to make of this. This is supposed to have been the weaker side. Nature is kind of shrugging its shoulders here and telling me contradictory things. So for my next idea, I was thinking I'd set up a Hall effect sensor using basically a Hall effect transistor. And so I wired this guy up. It works very nicely, but unfortunately it's got a Schmitt trigger in it, so it's meant to be basically a proximity switch, not a analog sensor like I had hoped for. And it kind of makes sense because I originally purchased these fellows quite a few years ago for CNC home switch work, and unfortunately, analog purposes wise, it doesn't work because it'll go from 0 off to say 5 volts on, whatever the supply voltage is. So fortunately, it acts purely as a switch. But the nice thing about them is they're a very precise switch. Given a particular magnetic field strength, it will, with the Schmitt trigger, go from off to on in a very sharp transition, a very square position, which is exactly what you want for precision, positioning indications. So if you happen to want to do switches for home switches and so forth, they're really easy to wire up. In this case, the manufacturer's part number is DN8897-ND. If you happen to want to do this, it's just 3 wires. Positive, negative, two leads. The white wire in this case is the signal, and it couldn't be simpler. It just goes to the voltmeter. So, being it won't do the analog value that I was hoping to do, I was hoping I'd be able to just go in here and go, yes, it's so many gauze. I definitely want to get some analog versions in the future for just this sort of thing. And I might even have one floating around here somewhere, but I can't find it, of course. So what I'll do is, being I have this nice setup already up here on my this little stage, I think I'll just do the same thing. I'll attach this Hall effects somehow. I'm thinking maybe 45 degree might work better, and bring it close to the poles of this guy in a very repeatable manner, and sweep it up until I get that trigger point, and then measure the distance traveled. And that might give me the most precise, repeatable value for the magnetic fields. I know I'm kind of probably over obsessing about this, but it's an interesting mystery as to why one side is weaker than the other, but otherwise, so far everything seems to be the same. So it kind of has to be the magnetic field. The coils themselves measure out the same. So that's about it. So I'll set this up to do some measurements and see what I can get. Okay, in the art of putting far too much work into something that really doesn't warrant it, I now have set up my Hall effect sensor, which unfortunately is an on-off Hall effect sensor. It's a switch, basically, not an analog sensor. Well, it's an analog sensor if it hadn't had the built-in Schmidt trigger, which is nice because it does produce a very crisp, precise, square on-off transition at a very repeatable nature. But unfortunately, it does require a lot of convolution here to actually use it. So the plan is I'm going to have this guy sweep up and down between the gap of these two pole pieces, always seen, because what it'll do is it'll turn on when it sees one pole, and it'll turn off when it sees the other pole, and then you'll see that switch go on and off basically between the zone of the transition between the two poles. So it doesn't really matter how far up and down I go, as long as I observe where that it switches, and then what I'll do is I'll move the travel back out further. So the trick will be, I have to get this edge right up against the edge of the pole piece, keep it repeatable, and then start backing this guy out until I see the field no longer enough to trigger this guy on or off. Or I guess I might do it the other way. Well, I guess probably makes more sense to go backing out, just keep backing out, and then get that measurement. So that's kind of the thing, is I have to now get this guy positioned repeatably against a pole piece, get everything reasonably square, just where it just touches, and then it's going to be, and then I have to zero this guy, and then start moving it back and forth until I eventually don't see a transition flip between on and off at the center point between where those fields basically coincide between the two poles. Hopefully that's all your folks are following that. It's weird, I have to admit, way of doing things, and all for no really good reason. Probably, if indeed it's a magnetic field strength, I can just charge up these magnets and move on with life. But I'm just kind of curious if it could be this. There's some other minor possibilities as I've been looking at this, that these poles, the plates don't seem to be quite parallel to each other, and the gap to the plane might be the other question. And, you know, I'll try a few other things. If anything, it's just kind of fun. Hopefully you folks are enjoying my obsessive checking here. Anyhow, we'll set this up a little bit more precisely and try and measure this. Okay, here's my setup again. This time I've adjusted the Hall effect sensor so its major plane surface is parallel to the pole faces there, instead of the 45 degrees I had it before. I had to trim back the heat shrink and so forth, and I have it set right now so it just barely touches this surface. Go back a little bit. Just barely misses it. Okay, so we're as zero as we can get, we're as square and centered as we can get for, you know, bubble gum and duct tape. And we'll try this again. We'll keep backing out till we don't see that transition occur anymore. Before I could only get out to about 10 thousandths and it would quit. Hopefully I can, since further along, I can get a little more useful resolution. Once again, I'm just looking for that transition at the center. And once I don't see that anymore, that's going to be my peak field strength for this setup. And once again, if I only had an analog version of this sensor, this would be a lot less complicated. I could just simply stick it right up there and say, yep, it's so many gauze. But I can't do that this way, so I just have to do with a physical measurement. Yeah, I definitely get more resolution this way. There's 50 thousandths. Okay, so that seems to be it right there. Let me go back a bit and figure out where that was at. There. So that was, it looks like 60 so far. 63. 65. 66. Okay. Looks like 66. Back to 65. There's always a certain amount of backlash to these mechanisms, so I may have to go back until I kind of get the lash out of the mechanism, and then once I see this again, I'll start backing out, and once it disappears, I'll call that good enough. Okay, so that was 62, right? 62. 63. We'll say it's 63, and I'll do a number of repeats on this, and we'll come back and do the right hand side. Okay, as you can see with all this tape on here, this is the right hand side. I got it once again zeroed to where it just touches that surface. You can see it translate. I got this all zeroed, so we'll start seeing where this field ends. We'll clear out 25 because I'm pretty sure it'll probably still keep working at this one. I'm going to clear out the 50 here. I'm pretty sure, hopefully it will be. Yeah, 50. No, we don't have 60. Yeah, once again, this is looking like this guy's weaker. Okay, we'll go back down to 50 here. 50. 52. 55. Exciting world of examining old tech in an overly elaborate way. 6. 7. 8. Yeah, 8. Well, it looks like it's 57. You could probably get a half in there if you wanted to, but okay, 57. Well, okay. What's kind of interesting is it's in the ballpark of the simple little sheet metal leaping up onto the face experiment I did earlier. So it's actually kind of interesting that they're both seem to be in pretty good agreement. I figured that this would have to be a little more precise and have a higher resolution and would tell me a little bit more. But it's looking like the simple method is just as accurate as this. It's kind of interesting. It'd be nice to, I hope to eventually get some analog Hall effect sensors, because I'd like to get an actual, you know, field strength and gauze for various stuff anyways. It's always been one of those things I thought would be kind of nice to have around for these sort of silly things. So I'll do a number of repeat tests to make certain this is repeatable, and I'm not sure what to do at this point. Okay, so after doing a bunch of mechanical kind of measurements to get the magnetic field strengths for these guys, it dawned on me that I did have a commercially made magnetometer available, so I was able to borrow its services for a short time and got these values. The poles were in agreement with my simple compass methods, and field strengths are kind of in line with what I've observed before mechanically. 65.9, 69.2 in the center, and 73.6 at the end there. And obviously you could just average those. It's just one of those things that's nice that you can just precisely put it over the various surfaces and see where they're at. It obviously isn't that important. 75, 71, and 69.9. You probably would expect the edges to have a little more field strength, because the edges, corners and edges tend to concentrate the field, which is not too surprising. And then the left-hand side is in a good agreement that it's a little bit stronger than the right-hand side. 80, 79.3, and 81.4, 74, 73, and 68.6 for the north side. Once again, the poles all agree. I believe even the earlier little quick experiment with the plastic film kind of indicated that there was a, you could see the in that plastic film with the ferrous material, that one side seemed a little bit thicker than the other. I hadn't really given it much thought at the time. I just thought the plastic was sitting there a little more closer to one pole than the other, but I might go back and investigate that too, just to get those last little details that are almost certainly not necessary, and determine whether or not you can actually see that with that plastic film. But I think you were able to, actually, so it's kind of interesting. So the next thing still to investigate is why one side's a little stronger than the other, and probably at this point, now that I got as much data as I can, it's probably time to see if I can increase the field strength of these poles with some strong permanent magnets. And I guess the thing is to determine how I might go about putting like a really strong permanent magnet across these poles and charging those fields. And I think I got some ideas as to how to do that. So we have our the head transducer speaker parts of our Brandy's headsets off, and we have them detached from the ear arm part there, and it's just easier to work with. We now have established our magnetic field directions, and we have a good idea what the magnetic field strength is. So the next thing is see if we can bump up the magnetic field strength and see if we can boost the performance of these guys. The assumption is that you know, after about 100 years, the really early permanent magnets, just simple iron magnets, I believe, they probably aren't even a particularly fancy alloy, has gotten weaker. And I know the old timers, they would simply say, well, you put your diaphragm on there and you take and shake them upside down, and if the diaphragm falls off, you know, it can't be held on by the magnetic field, they're too weak and they need to be kind of, the magnets need to be recharged. And of course I've gone through all this extra effort to kind of characterize the magnetic field strength and everything. And mine, I do believe, you can shake them upside down and they will not fall off. Well, now they said that. I thought they held on better than that, but I guess they don't. Okay, all right. So I guess from that standpoint, the old timers are saying that needs to be recharged. Okay, so I guess it was. I thought I tried that earlier and it didn't fall off, but it apparently does. I'll actually try real quick the rusty one, because I think this one goes with the one with all the tape. Will it fall off now? Oh, that's okay. Well, that's interesting. What does that mean? Okay, so let's try the one that I believe goes with this side, which, you know, by all measurements, the magnetic field strength is stronger. Okay, we have a new mystery. And I finally got it to come off, but that was quite a shake. That's an interesting mystery. So what does that mean? You know, the magnetic field strength on this guy measures weaker. The magnetic field strength on this guy measures stronger, but acoustically he's definitely measures weaker. He measures stronger. About the only difference between these guys is this one's a bit rustier. Maybe it's bowed a bit. It surely looks flat, and it doesn't seem to grip as. Did I try that combination on this side? I don't recall if I did or not. It'll come off this side. All these permutations, you gotta. Okay, so. Alright, so I think I've tried. Okay, so I guess from a magnetic field strength standpoint, old timer mode, they would say then that this one's weaker, which certainly looks like it is, and that this one is stronger, but it's acoustically weaker, so very puzzling. So I guess if anyone needs recharging, it's this guy, and it kind of by the shake test, that's kind of what you would think. So I got a get my little magnet and my compass out of the way. I think the other thing to be aware of is that it's 2,000 ohms of very fine wire, so that's a crazy amount of wire in there, and if I put a permanent magnet onto this guy, it might induce a heck of a current. So I'm going to keep these guys very far apart so I don't induce a current, possibly burn out these coils. So I have my permanent old permanent magnets from a I'm not sure what this was from, a really early big hard drive, I believe. And so like poles attract, so if I take the south to the north and charge it up, we'll see how this goes, I guess. Oh boy. So I guess the question is how to go about it. Do I just set it there? Right now I have it set on the pole where the field comes up, and I got it next to the that side. It seems very happy with it. So I think what I'll do is I'll just let it sit there for 5 minutes, and then I'll put the other pole on the other side for 5 minutes, and then I guess I'll set up my magnetometer arrangement. I might do the old timer test too, and see what we get. See if this makes a difference. If it does, then I'll do it to this side, and it may be as simple as that. So I'll come back in a few minutes here. Okay, so south to north, we'll go again. Another 5 minutes. Okay, so that's been 5 minutes on that side. For the right hand side, let's measure this guy and see if it makes any difference. I guess one of the first things I could do real quick would be let's get the old timer test here. Let's see if that feel any stronger. Don't want to fall off. The other diaphragm. Yeah, at least from that standpoint, they don't fall off. So before they were wanting to fall off, so that kind of indicates something. Just do it more scientifically, though. Okay, so I have my headset right-hand side mounted in my little test fixture here with the Hall effect sensor. That's unfortunately a switch and not a analog guy. So once again, I have to move the stage back by this micrometer to measure the actual field strength. When it finally gets to the point where it's undetectable, the Hall effect switch goes on and off when it goes past the transition here. And being last time I was at 57 thousandths, let's just go ahead and back this guy out to that and see what we get. 25. We'll set it at 50 here. We should still see that. Yeah, 60 is what, 63 is what the left hand side was at. Okay, so there's 75. Hopefully it's going to be greater. Alright, so we're already greater than we were before. I believe 95. Wow, we're way out there now. Okay, there's 100 thousandths. Okay, 100, lost it at 115. 110. 105. Okay, so we got 105 thousandths. Well, it looks like 106 thousandths. Okay, here's a bit of lash. There it is. Okay, 100 and it was right on the hairy edge. Okay, go back one more. Might work. Yeah. Okay. 105, 106. Let's see if we can get 160. Okay, we'll say 105,000. So that's pretty good. That's, you know, just about double the distance. So I'd say that's definitely charged up quite a bit. The question is, of course, is that ultimately what it can do? I would think that the permanent magnet, the modern permanent magnet, is going to be quite strong, and it would saturate the iron of these old iron horseshoe magnets to the point where you couldn't like overcharge them past what they originally would have been capable of. They're only going to accept so much flux, and that's going to be it, I would think. So it'd be interesting to know if there was some way of proving that, but it's nearly double. And my guess is if I do an audio test next, I'll find that it's not a linear result out, but it's going to be definitely a greater audio output, I would think. So that might be the next thing to do. I guess the question is whether or not to do the left-hand side or just do the right-hand side first. I guess I should probably just do the left because I can't see any reason not to. Okay, so here I have the left-hand side, and I've managed to charge it up some. I think I've gone from 63 to about 80 thousandths physical distance, not in gauze still. What I did on the right hand side is probably the proper method, which is of course you take the unlike poles, opposites attract, and I slid it towards it, attached it, and then when I was done I slid it away from its pull piece. But I think what I did on the left hand side is I approached it carefully and attached it to the surface, but when I was done I simply pulled it away, and I think it scrambled the field. And I seem to recall vaguely that that's the method you do to charging magnets, is you don't pull the faces apart from each other. You take the major pull faces and you slide them apart, and I believe that's what you're supposed to do to keep from being scrambled. And in this case, this last time around, being I already have a north and a south and a south and a north. So I guess I can actually go this way, don't I? North to south, south to north. I simply slid it on and used both poles. Maybe I'll do it this way, it's a little easier to look at it. Okay, so south, north, north, south. I did is I approached it this way, and I got across those two poles, and I'm just doing a charging both of them at the same time. So, okay, hopefully you guys saw that. So basically I have, now I can't remember who's who, completing the circuit this way across those poles. So that bumped it up by an amount, about what, almost 20 thousandths travel distance, and that was after 5 minutes of charging. So I think what I'll do is I'll charge these again for another, I don't know, 5 minutes, 10 minutes maybe, and I will then measure this yet again. And once again, what I'll do is, instead of pulling it apart, I'll slide it out away from each other. And I seem to recall basic 101 on magnets was, I think that was the rule, that you don't pull the poles apart. You kind of slide them away from each other, and in that way you keep the field from being randomized. I think the question mark here is, of course, there's two horseshoe magnets, and it's a kind of odd way of doing it because you would think they're bucking each other. because they have two like poles facing each other, and it's one horseshoe magnet and a second horseshoe magnet. It seems like an odd way of doing it. You'd think it seems unideal, because I was under the impression you don't really want like poles, you know, sitting against each other. Let's see, I'll grab the other guy here. So basically what I'm saying is I guess keep that magnet with that magnet. You have a horseshoe magnet here and a horseshoe magnet here, and the two norths are presumably being held in place by this little pole holding plate, and ditto with that side there. So if I apply a permanent magnet to one side and then pull off, I have to hover over this one horseshoe magnet doing that. Does that cause troubles? I'm not sure. See, what I was doing before is I would slide them across here and then slide it back off, and for this guy it seemed to work, but for the left hand side I pulled it straight off. Maybe randomize that. It might still be better for me to slide it on and off with just one magnet on one side, because if like I say, with these two magnets, I might be scrambling things if I pull it off this way. Those little details in magnets, you would have thought they'd be so complicated. Charge that for, give it 10 minutes. I'll slide it off and I'll try measuring this again. Okay, quite a bit of time later, it's pulled this guy off, supposedly the way to do it. And I'll measure this guy again. Okay, one more time. Hopefully this time I used two magnets, slid them apart carefully and so forth, but I may be just overthinking this, and it's simply maybe that this is the saturation of what the old permanent magnets can take, and that they weren't really all that weak to begin with. So we will do our little switch here. That just touches. Zero there, pretty good. We'll go out to 50. There's 50 there. 60, 70, 75, 80. Okay, so that's where I had petered out last time. 85. Okay, so I'm making progress. 90. Oh, this is looking better. 95. Yay. 100. Okay. 105. Yeah. Okay, so, and the right hand side had come out at 105, and this is coming out at 100. So I think we're in the ballpark of maybe where we're going to get is all we're going to get. Okay, backlash issues here again. Let's see if I can see this guy. There you go. Okay. 100. Okay. Back to 95. Okay, 96. 97. 96. 95. Okay, 95. Okay, so 95, I guess, is all I'm going to get on this guy. 96. Come on, 96. 97. 98. Okay, 96 then. The backlash. It's hard to come back there again. 96. Okay, there's 95. 96. Looks like it's 96. Yep, 96. Okay, 96. I'll have to think about what in the world I just did. I did a whole bunch of different putting magnets on, putting magnets off, and but I think that's probably it. I might try and some other stuff, but that might be it. That might be the maximum saturation magnetic field strength that you can get on these guys. Okay, without going into too much tedious detail, the left-hand side measured out pretty close to that of the right-hand side. Probably about, let's see here, the mechanical gap for the Hall effect sensor measurement was 0.96 thousandths as opposed to 105 thousandths. And once again, I was able to borrow the services of the commercially made magnetometer for a few minutes. And on the right-hand side, it's in pretty good agreement at almost exactly 100 gauss on the right-hand headset, and on the left-hand side, it's pretty much 100 gauss also, maybe a few gauss lower on, say, the North Pole and a few gauss over on the South Pole, which makes me kind of suspicious that I've actually magnetized and saturated these magnets to pretty much what they could max out to, and that was probably an original engineering goal that Brandeis is probably using. It was kind of one of those cases where, you know, you assume back in the day they just kind of randomly built things and just kind of stuck with it, and whatever worked just kind of worked, and they didn't engineer this stuff out. My suspicion is that they probably did specify magnetic field strength, because it's a heck of a coincidence that if you measure right at the faces of these poles where the where they're making the interaction with the steel discs, it comes out right at pretty much 100 gauss, which makes me suspect that they specified that as a manufacturing specification. Probably the actual horseshoe magnets, if you were to actually measure further down past these little pole bracket pieces that go up through the solenoids, you'd probably find that they're a little higher strength still, maybe I don't know, 10-20%. I'm not sure how much loss you have going up through the ducting, that is where the magnetic field up through the coils from the actual horseshoe magnets. But it looks very suspiciously to me like Brandeis was probably wanting 100 gauss at the face of these pole parts going up to the steel discs. It's just a heck of a coincidence it's 100 gauss. And while I was at it, I was able to measure the big permanent magnet that I was using for magnetizing these guys. And it turns out they measure out at around 2,500 to 2,600 gauss. So it's about 26 times more powerful than what I wind up with at the headset pieces, which indicates to me that the really early magnets obviously weren't the most strongest things in the world, and you probably do have the material saturated to the maximum field that they can basically retain. And once again, if it's 100 gauss, that's just too much of a coincidence. I mean, I guess it's conceivable that it really wasn't planned to be 100 gauss and it just happened to come out that way, but I find it just kind of remarkable. So I feel kind of confident that I've probably magnetized these guys about as good as I can get, and that's probably their original performance magnetically is probably what I have right now. Okay, so here's the results after, of course, magnetizing the headsets and then running the signal generator through them. And as you can kind of see, it's quite a jumbly bunch of lines between the old and the new, so probably easiest thing to do is break it down to right hand side versus left hand side. So on the right hand side, you can see there's a bit of a performance gain, not dramatic, and in fact you could even argue it's slightly less, perhaps the higher frequencies, and that might have something to do with the stronger field strength. And I was kind of wondering if that might be the case. The stronger the field strength, the more you might lose out on some signal and gain on other signal, and it's kind of indicating to me that the lowest frequencies you gain still more with the higher field strength, and you lose with the higher field strength at the higher frequencies, which does kind of indicate that you can't just simply put massive huge magnets in these things and expect proportionate gain at all. And probably there's a diminishing return, and that might be it right around 100 gauss, if indeed that's what was their design goal. It's a lot clearer on the left hand side that we definitely gained quite a bit. The left hand side was already weaker than the right hand side, so it certainly needed it. And in fact, it looks like the left hand side is now stronger than the right hand side, even though the magnetic field strength when I measured is a tiny bit lower field gauss, not by much. So it's interesting how much better performing sometimes these headsets can be from one side to the other. So it indicates they're kind of squirrely technology of the day. As much as I'm sure Brandeis Brandeis tried to make their headsets as reproducible and balanced and matched to each other. They probably never were anywhere near as matched as, say, any sort of modern technology you would expect today. It's just, it's such a challenging thing. You have relatively few items to work with, and very little in the way of dampening control back factors, like in this case it's just a steel disc, and you don't really have much in the way of other further controls other than magnetic field strength and of course the current going through the coil of wire. And then you got little variables that I'm constantly been wondering about myself is how tightly do I screw these caps on? How much do I compress the disc over the ear caps? Stuff like that is vague, hard to determine, and probably varies quite a bit over time. So I find kind of cool and encouraging that I can take some really crude mechanical methods and double check it with commercial equipment and have, I think, a pretty good idea of what was going on about 100 years ago. So, mechanical, old stuff like this is kind of fun to play with just because it was cutting edge in the day, and it's kind of easy tech to play with today compared to other stuff. So, to me anyways, this is kind of a fun project just for that reason.